Okay, so we'll have the last lecture of the manual and one section of the workshop.
Thanks. Okay, thank you very much. So let's start finally. Today finally we're going to describe the most general method of doing quantity localization. So this is localization. One localization via L1 optimum transport. Very recent work by both last summer. Okay. So basically, this method kind of combines, I think, the advantages of the geometric theory approach, which applies to manifolds, but only for a very specific F balancing function, curvature function. With the bisection method that we saw yesterday, which is very general, but only kind of applies to our analytic symmetric situation in the sphere as well. Okay, and indeed the construction is finally connects maybe to more mainstream interest regarding to optimal. So again, setup as usual is that we have a smooth connected manifold. Doesn't have to be complete, doesn't have to be oriented. It is crucial that it's geodesic convex. Certainly, if you're doing optimal transport, that makes sense. You want to make sure that the neutral relationship stay inside the manifold. And we have a measure, have density with respect to the Riemannian volume measure. So part of it seems that it's infinity, but I think there's nothing in the proof that really requires it. So it has to be positive. So it's enough. Just we C2 on the manifold. Okay, so here's the theorem. Says the following. So indeed, the f is an L1 function integrated to 0. And here's the only kind of technical assumption. So this is a totally minor technical assumption that we didn't see, let's say, in the bisection method. So it needs to assume that, again, coming from optimal transport, it's going to be immediate while we use this. It's fine at some point x naught, right? Okay, it's like the first integrating that with respect to you weighted by this additional factor. Okay, and of course you're used to this type of condition when you're working with right W, the space of probability measures P2 having 2 second moments, you screen that. Right? So this is like a P1 condition. Right? You want the first moment of the measure to be finite. I mean, you want it actually to when you integrate it against F to be finite. Okay, this will come up in an obvious sense, but you can have to work around that if you're doing applications. So this is going to be only small technical thing needed. Then, okay, the resist, so let me write it this way. The resist will affect measurable set S subset of your manifold such that one. So outside of S, F is equal to 0, mu almost everywhere. Okay, so if you will, S contains the support of F. So outside of S, really F vanishes, and it's not too interesting to localize a zero function. Okay, if you want to write a localization of a measure on a region of the space where the function is just equal to 0, then of course you can do it in any different one. Okay, the balancing condition is true. Okay, so this part of the space is not interesting. Okay, second is that there exists an F balanced localization on the of alpha, the measure mu, restricted to the interest in set S. Okay, so as usual, mind you that what does this mean? Localization, right? It means things. It means integration condition, right? You restricted to S as this type of disintegration where the measure lambda, its appropriate sigma algebra, and mu are complete measurable space. The balancing condition is that indeed mu almost of alpha equals 0. Okay, and finally the localization property. So maybe I'll expand on that. Just introduce the localization. 1D localization. What does that mean? So 1D localization. So continue. Means well, it means two things. It means that there exists a full set of indices having full measure such that just mu alpha. Well, just it's the usual thing, just to kind of call notation for any alpha in the good set of needles. I need mu alpha is 0. So it means it's just supported on a distance minimizing geodesic. So gamma alpha from some open interval. So the point I wanted to emphasize is this L alpha is open interval. Subset of R going into a manifold. And the geodesic, of course, as usual, is characterized by R times. Okay, and second is that indeed all of these guys are disjoint. Okay, so that's the what 1D localization means. So in other words, the disjoint union of these geodesics is indeed a mu almost everywhere partition of S. So you have your pictures. You have your manifold, and there's a set S, which is not interesting because here F is almost everywhere equals 0. And the rest of the space localizes. You can partition the interesting part of the space to some composition so that the F balancing condition is preserved. Okay, and indeed it's a partition up to an eligible set. Okay, now what about the density, right? We want to say something about the density of these needles. So this is number 3. Density now, so for any alpha in this, let's say, good set of indices of needles, mu alpha has the following density. Okay, if they want to, so maybe I call, so again, usually I identify between the measure on the needle, the geodesic, and the measure on the Riemann. So if you want to be correct, you say it's pushed forward via the geodesic gamma of this density. So this is the density on the integral L alpha. Okay, where that density has psi alpha that can be written as so satisfies psi. So it's the density on the geodesic. Right, this is exactly the way we saw it in the yesterday when we were doing the bisection method. So it's the original density times the Jacobian factor. Times the Jacobian factor. Right? With the alpha being smooth, strictly positive, now alpha, and what does it satisfy? So yesterday we saw it in the repeating case, J alpha raised to the 1 over n minus 1 was concave. right? Which is a manifestation of the fact that it was the limit of these uniform measures on convex sets converging to it. Here, the anomalous condition would be very naturally that minus logarithmic hashing with index n-1 Jacobian is good. You know, in that room, right here, minus logarithmic hashing minus 1 the Jacobian is bigger than, if I write bigger than 0, this is exactly by definition means that J alpha to the 1 over n minus 1 it is concave. Okay, but here we're a manifold, so the intrinsic geometry of this manifold comes in, and it would govern is the Ricci curvature of our manifold at the point, at this point, in the direction given by the geodesic at the corresponding place. So recall, it's not going to be used, but this is a logarithmic hashing of a one-dimensional function. The index q is equal to two derivatives of 1n. So it's the logarithmic hashing plus 1 over 3. Okay, that's the answer. So indeed, this minus 1 hashing being non-negative means that the function to the power of 1 to the power of 1 over q is concave. But in general, if you have some normal bound, it satisfies this. If you want, this way as well. Okay, so you see the concave after the 1 over q from this equivalent, completely equivalent definition of the logarithmic hashing. Okay, so what does it mean? In particular, this means that C0 n gets inherited. So if, as we expect, if this satisfies C0 n, and n is in the right range, then all the needles, all of these guys, CBT, will satisfy C0 n. So we did this already twice. Why is that? It's because this density psi alpha, right? It's a product of two terms, and we had this kind of lemma 2 days ago on the slides that said that if you have control over the logarithmic hashing of this guy from below, minus the logarithmic hashing of this guy from below, and of this guy from below, and if the indices sum up so that they're in the right range, which exactly boils down to capital N being in this range, okay, then you can combine this information. And that's exactly what's going on here. You can control the logarithmic hashing of the Jacobian. By definition of the manifold C0 n, you have control over the Ricci minus the logarithmic hashing of the density, and then when you combine them on the right-hand side, you will see the n-dimensional Ricci curvature tensor, which is assumed to be greater than rho. So we did this already 2 times. Anyway, it's exactly as in the resection method, as in the geometric theory method described 2 days ago. So C0 n gets inherited in this result. Okay. By the way, so I'm kind of being fussy here about the set S. If you want to, so here the point is that this interval is not empty; it's open. Where's that from? It was an open interval, right? So non-empty. Okay. If you want to then have a localization of your time space, then you can just degenerate your interval into a single space. Okay, but then it's not single point is not open. But then you just add these single points. Okay, you add these single points to your decomposition, and indeed, of course, the balancing condition is satisfied. And this is actually, maybe I kind of skimmed over this part yesterday, but this is exactly the situation that we have in the bisection method. Because remember, these convex sets were degenerating into something which is either one-dimensional or zero-dimensional. So I forgot kind of to say that some of these needles that we get with bisection method are 0 dimensional, so they're just single points. But they're not equal. Here I am kind of making a point out of distinguishing between really the 1D guys and the 0 guys, because this set S has actually meaning. Okay, so that's why I make this like this. Okay, so what's the idea of the proof, right? So this is what we want to do today. Describe to you how this method works. So any questions about the formulation or the doing business? Yeah.
One question about the architect method. If I correctly remember, you defined these lambda, nu, and A as a metric method space. So
Was it metric?
I don't know.
No, I don't. If it's a metric, it wasn't a complete measurable space.
Oh,
Maybe it was a Freudian
okay.
complete measurable space. There's
We
no.
don't need
Yeah. So really, well, I mean, this is kind of a general thing in measure theory. What this space is actually this index set is actually the index set of this measurable partition. What you really get here is a measurable partition. So there's this theory of disintegration using measurable partitions. Indeed, the way we're going to obtain these geodesics is not via bisection, because we don't bisect the manifold, but via some equivalence relation. So we're going to construct this partition. So I don't see any use of remembering the fact that this index lambda is actually comes from quotienting out and with some equivalence relation, but that is indeed the case. This index lambda actually is an equivalence, is the equivalence class under some relation which we're going to describe. Yeah, so there's no metric, interesting metrics. Okay, so the idea of the proof. So first of all, let's forget about the balancing condition. We'll worry about that later. So observation, going back to the work of Evans and Gangbo, observation. Is they worked on L1 optimal transport as well, and the version is that any one which function what would say? So of course I'm going to just write it out. That induces the emphasis is partial decomposition of composition into those. So here's the definition. We're going to call strain of U, so Z belongs to the strain of U. So I'm using the notations by Hartog. So suspension, so strain kind of, you'll see what it is supposed to signify if there is X and Y, which are not equal to Z, it's important, so that basically Z lies on some distance minimizing geodesic between X and Y, and the function U increases as fast as it possibly can. It's one Lipschitz, so it only increases with rate at most 1. It really increases with rate 1 here. So such that, so just write this, UZ minus UX is equal to the distance between X and Z, Y minus UZ is equal to the distance between Y and Z, and indeed the distances add up. So it's really distance minimizing the rate. Okay, so in words, U increases as fast as we can. Sorry? So this is the definition, and somehow this condition just ensures that really you get a relatively open kind of geodesic. Okay, so example, this is an example which we already saw 2 days ago, in a sense, is that if you take u to be the distance function x from some, let's say, hypersurface S, then, okay, by the triangle inequality, this is one Lipschitz. Okay, and so this is my S. So if you start looking at the strain, is exactly given by these rates, where of course it increases as fast as it can in the orthogonal direction to the surface. But at some points, let's see here, maybe you got it better. See, it goes here, but then of course it will stop increasing as fast as it can when it reaches the focal point. Okay, or if it reaches the cut locus. So this really will give us. So the strain is really everything in this case. So in this example, the strain is everything except for the cut locus, which we know is a negligible set. Okay, so this is the definition of the strain, where U is kind of strain, right? So the meaning is doing the best it can as fast as it can. Okay, but of course, for a general Lipschitz function, it doesn't have to be the strain doesn't have to be the entire space. Maybe in some parts of the space, it's only half Lipschitz actually. So then you don't count that part. And here's a fact. So here's an example. Here's a fact. First of all, the strain. So strain is a measurable set. Even the well measurable thing. It's a measurable set, and on it, we can define the following equivalence relation. Following equivalence relation, x equal to y, if and only if. So I really want to get as equivalence classes these kind of maximally strain geodesic. So just define this ux minus y is equal to this y, right? Because it's one Lipschitz, this means that really u is completely straight. So this example, the equivalence classes would be indeed these rays, right? Until it reaches the cut locus here. These will be the equivalence classes. Okay, all the points along this map. Equivalent, and you can show that each equivalence class which we call gamma alpha, and will be the gamma alpha in the theorem, is a distance minimizing and relatively open to this. Okay, so these are basically it's an exercise. It's not basically it's obviously from the picture. Okay, but at least it gives us a very nice way to kind of do this needle decomposition, just given at least on part of the space, if you start with a one Lipschitz function. And really, Clark's theorem consists of 2 parts. So really, the first theorem, which was this is the technical part, okay, is to show that for any one Lipschitz function u, we obtain the preceding theorem, which is written above. We obtain this theorem with what? With the set S being the strain of u. Okay, so that's why I wanted to emphasize this S, single out S. I'll tell you what I mean by this. In other words, we get that u restricted onto the strain, and these decomposes into these measures, which are u almost everywhere supported on the equivalence class.
What you can answer preceding?
Theorem.
Theorem.
Yeah.
Thank you.
Yeah, this theorem. So in other words, I can tell you what I mean by this, just to show, without repeating the details. So I can, we have this integration. First of all, each of these guys supporting these terms geodesics, so it's really a 1D localization, and the CD rho n, that's kind of the same thing. So, and really, you have this property with a density, but for applications, if you're interested in CD rho n, it means that the CD rho condition gets inherited. So L alpha, yeah, I can write this in level of geodesics. Yeah, we got. Right. So I wrote it here on the level of geodesics on the manifold. There's isometric, there's isomorphic to writing it on the integral L alpha. Okay, so CD1 information gets inherited. And notice here, this is completely unrelated to any balancing condition. Okay, so there's no balance right now. What's the idea here? So this is a very technical endeavor, but the idea is this here. So this is now getting closer to non-smooth analysis, which we're working on. So on strain view, observation, basically going back to Feldman and McCann, says that U is differential.
Just one question about the replacement of theorem. So you said that preceding theorem here we have this geodesically convex, so strain should be, I mean, we need all of these conditions for this S to have.
No, but here the condition was on the manifold, geodesically convex.
For S.
Okay, S is not geodesically convex. Maybe my picture was misleading, but the original manifold is geodesically convex. Okay?
Yeah, there is a direct measurable on S. Yeah, I thought that on okay.
Geodesic convexity is hidden everywhere inside because anytime you want to kind of interpolate, you don't want to leave your space. So it's a way to not say the word complete. It's a way to kind of disregard what's going on in the boundaries. So completeness is kind of two things usually together, right? So it's the fact that you can extend your geodesic indefinitely, right? And it means that between, and there's a theorem that between 2 points, you can have this is minimized geodesic. So we just want the second property. We don't care about if you can extend geodesics indefinitely. Particularly, we don't care if you drop off here if you reach. So I'm missing that. Okay. So on strain U is differentiable. That's pretty cool. If it's differentiable, so I should write this as basically the third one.
So do you mean that S is strain of U or M is strain of U?
S is a strain of U. So again, U is an arbitrary Lipschitz function. So in some parts of the space it could be just half Lipschitz or constant. It's definitely not strain. Strain means that it's increasing as fast as it can in that area. Okay? But on the strain of U, that's why we took it relatively open. U is differentiable. And of course, if it's differentiable, then of course its gradient has to be equal to the underlying geodesic, right, X. So you can look at the alpha, which the geodesic in which X, the point X lies, and of course it has to be pointy. It has to have the unit one speed pointing in the direction of the geodesic. Okay, but the whole point is to show that it's differential. Okay, and now the main kind of idea of Clark-Type. So Clark-Type is an expert on the Whitney extension theorem. You wrote about the Charles Pfeffer. So the idea is to use. So that's kind of a very smooth thing to do, but to use Whitney's extension theorem. And here we go. Okay, I think I can erase this because because just gonna be saying this. Okay, so fix this. Okay.
Can you slide up the back?
Sorry?
Slide up the back. So
Sure.
look at your body. Sorry. Sorry. I didn't-
No.
In your definition of strain, you say U increases as fast as it can on X tending to Y. There's no use of Z there. Where's Z?
No, I'm saying C belongs to the strain. If you can find 2 points, different points.
But also U is one Lipschitz, so
Yes.
so it's clearly increasing as fast as the U.
If it's 1 Lipschitz, the fastest it can increase is at a rate of 1.
Can't be on the edge, and it has to be between 2 points where U is increasing.
Okay.
Yeah.
All right.
It could be empty, right?
Sorry?
Yeah.
The strain? Oh, it could be it. Take a constant function here. Is that?
Yeah.
Yeah, for sure. That's why, I mean, okay, it's a very technical theorem, but then, without the balancing condition, well, how does it help us? That's the second part.
Yeah, but so how do you want to find like a strain as big as you want to do?
Yes, you want, well, what you do is make sure that you have the balancing condition. Okay. I mean, if the balancing condition will automatically tell you that the strain ends where F is supported, please, because otherwise you cannot ensure that the integral of F is equal to 0. So the fact that strain will be in the interesting part of the space will be ensured by the balancing condition. If F is equal to 10 somewhere, I cannot. The strain has to pass through it so that it integrates to 0.
That's exactly Gromov-Wolff-Poulin, actually. Isn't it?
What?
That's exactly Gromov-Wolff-Poulin. Exactly what they mean in this paper. It's precisely that. Yeah, I've seen it.
I don't see the connection.
It's absolutely that.
Well, there's no
Yeah.
topology.
Well,
So
in
it's
case
really
you
one
have
deep-
topology, what in the case, for example, in the sphere, what Gromov did exactly is that prove that there's always a strain, and always a fiber going to the strain. That's why you can do the localization. Here, since you don't have the, topology, I guess you have to do this Lacan.
Okay.
Yeah,
in
that's
this,
what I mean.
in this sense.
Yeah.
But this is very particular to 1D. I mean, Buzz will eventually generalize this theorem to symmetric spaces or something to get higher dimensional needles, but in general, you cannot expect to have a high dimensional version, whereas the bisection method does.
Absolutely. Yeah.
Okay, so what does he do? He says that using within the extension theorem, there's a C11 function. He does it locally, but actually using the partition of identity, he also remarks that if you want, you can find a function in the entire manifold. So C11, of course, right, means that it's differentiable and the derivative is Lipschitz continuous, right? So you can find really a C11 function such that, or U tilde such that if U tilde and its derivative, now the U tilde coincide with our data. So we need on what? So on almost the strain of U, you have to take an epsilon here. So epsilon here means you're epsilon away from the boundaries. Remember the strain consists of these equivalence classes, which are relatively open geodesics. You take an epsilon distance from each of the endpoints of this geodesic. Okay, that's what you need in order to be able to apply Newton's theorem, with control over the second derivatives. But anyway, the point is that now you're in business because U could have been an arbitrary Lipschitz function. That's not very. The idea now is you want to kind of, if we knew that we were in the smooth setting, then we could just take a look at level sets of U. It would give us a smooth hypersurface, and then we know that basically locally U goes like that, and we could repeat the smooth calculation that we did on the slides two days ago. The problem is that U is just an arbitrary Lipschitz function. Okay, I mean, it doesn't really make sense to talk about the normal. The normal could have some discontinuities. I mean, its level set could be like this. Okay, so when you're doing some extensions, you're missing stuff, and you know it's a hassle. But it turns out that you are actually it's not C2 yet, it's C11, but already you gain one level of differentiability on the string. Okay, that's the main idea. On the string, you get one level of differentiability, and now for C11 functions, you can basically repeat all the Jacobi calculations. That we did. You look at the math that t equals the exponential of t nabla u tilde. Now, right, this would be the math, and you do exactly the same calculation, and you extend from the C11 hypersurface, not C2. And that's pretty technical. I mean, I'm sure that many people here, most people would feel comfortable with that, but you know, instead of doing just a classical calculus, you need to work with Lebesgue density points of the string. You need to use Lebesgue differentiation theorem instead of the fundamental theorem of calculus. You need to use, instead of, let's say, convergence theorem, use the Lipschitz version of the divergence theorem of, I think they're going back to the Georgi. Even something which is kind of obvious, which is that in the smooth, when U is C2 smooth, then its second derivative, the fact that it's a symmetric tensor, which was that's actually important when you're doing these rich data calculations. You're doing some Cauchy-Schwarz inequalities. Even the fact that this is symmetric is a lemma. I mean, you need to show something is symmetric, you know, almost everywhere it exists, and so on. Okay, so that's very good. Okay, but anyway, so C11 brings you, to the starting line, and then you still have to work, but it's doable. So this is how you prove theorem one. Basically, the calculation which was classical and easy in the smooth setting that we did 2 days ago once. Okay, so that's as far as I wanted to speak about proof of theorem number one. Okay, now this would be kind of useless to our applications without theorem number two.
So sorry, your exponentiation here this is a smooth metric.
The manifold itself is smooth. The manifold itself is assumed to be smooth. If you really want, you could bring it down to some CK, maybe C3 or whatever.
But then this thing that you're getting is Lipschitz.
Oh yeah, for sure. Yeah, U is C11, so really the normal here is Lipschitz continuous. So at least it's continuous. At least you're not missing anything out. But still, it's differential almost everywhere, and you have to work. Okay. So again, theorem two, which addresses the balancing. So the question really is, maybe theorem, that's a question. So given F, which is balanced, given F, which is balanced, which you apply to, which you need to use in theorem one. With theorem one, you want to find a U to use it to, so that we get the F balancing. Okay, and the answer, following part of the answer motivated by Evans and Gunko, is to use maximizer, the following optimization problem, which should look familiar to you, max over the integral. So F is given, right? So maximize over the integral of F times U d mu over the set of all U1 Lipschitz functions. Okay, so you're given F, you're trying to maximize over these Lipschitz functions. This guy, of course, by the way, the maximum is attained. There is a maximizer that's given. By the way, this is where you use the technical assumption that I mentioned before, obviously since U is Lipschitz and increases no faster than the distance, okay, that's why at least you know immediately from that assumption that this guy, the supremum is finite. So the finiteness uses the fact that the integral of f, the absolute value, the distance from a point dmu is finite, right? So this means if U is Lipschitz, it's going to be finite. And then by an obvious Arzelà-Scully theorem, so you can restrict the compact sets, you can always assume, since f is balanced, then changing U by a constant doesn't do anything to this integral. So you can always assume that U is equal to, if you have some sequence of functions trying to attain the supremum, you can always assume that they're equal, that all of the sequence is equal to 0 at a given point. Okay, so that's on a compact set. This means that you have uniform validness and you have equicontinuity because it's fully continuous. And then by Arzelà-Scully compact set, you know that there's a subsequence. And then by taking exhausting your space with compact sets, using this kind of regularization argument, means that you have a maximizer on the entire space. Okay, so no problem with that. That's an exercise for students. Okay, so it does exist. But how is this, why does this help us? To see that it helps us, I hope that already you figure out what's the connection to L1 transport. So we call by Monge Kondrovich duality. We know that the L1 distance, W1, between these given two measures, mu1 and mu2, is equal to, so by definition, that's equal to, let's say, let me use maps instead of measures on the product space. Let's say mu. So among all maps pushing forward the first, let's say we have two probability measures. Among all maps pushing the first one to the second one, so that the L1 average, not the L2, the L1 average distance of the transport is minimal or infemal, then this is equal by the duality, the supremum over all one Lipschitz functions when you integrate mu 1 minus mu2. Okay, that's the classical duality. Okay? So what does this tell us? This tells us that actually, this means that maximizing this U over here is actually solving. So maximizing U in this problem is Kondrovich potential for the optimal transport problem, L1, transporting, it's transporting the positive part of F, U onto the negative part of F. So I take the negative part, so the sign, negative. Okay, of course these two have the same mass because of the balancing condition. Since the integral of f d mu is equal to 0, these two have the same mass. At least everything makes sense. I have two measures having the same finite mass. Yeah, this interval has the same finite mass. From this measure to that measure, I can look at the optimum transport problem AL1. Look at the Kondrovich potential U. It's going to be, by definition, it's a maximizer of that, right? It's a maximizer of that. It's factorization. Because here what's written is exactly d mu. Okay, f plus mu minus f minus mu is exactly f d mu. Okay, so yeah, so maybe you got a picture. Right, so I have the part of the space where f is positive, and the part of the space where f is negative, and what I'm really getting is a picture like that. We do the optimal transport, and it's known that the strain of U in this case consists of all these one-dimensional optimal transport rates. It consists of the mean of all needles, which are optimal transport rates, among which F plus gets transported to F minus. So for each such a needle, So really, the way that the optimal transport works is along each needle, the density, not the density, but the measure here, this kind of distribution gets mapped onto the measure there. But what does it mean? It means exactly that on each needle, we have, if it's transported from here to here, they have to have the same mass. So this means that F plus mu alpha has to be F minus mu alpha. In other words, it means that is equal to F. Mu alpha is equal to 0. Okay, so somehow using the interpretation, the geometric interpretation that along these equivalence classes on the strain, we know that this is exactly how the optimal transport does its business. It transports it like that. This means that actually you get a balancing condition. Of course, if you want to make this kind of rigorous, then okay, what you can do is say, assume if you want to kind of say that mu almost everywhere, so mu almost every alpha. If you want to say maybe let's try to prove this. So if this were wrong, this would be almost a positive measure where this is false, and then you can, by perturbing u, you could actually get a contradiction to the fact that u is maximized. That's how you do it more rigorously. Okay, but this is the geometric intuition. Okay, why you get the balancing condition. Okay, so that's all I want to say about the proof. And now, so first of all, this L1 business is very interesting because it goes against what people have been doing in the last. I mean, and at least when you're working with the same condition, there's always been using the L2 distance, also various proofs. So you can use optimal transport as we know to get various things, various functional, isochronometric, and Minkowski inequalities, and always the L2, or almost always, it was the L2 distance that was being used.
So can I just ask, so the reason that the L1 distance comes in here is because you're looking at the integral of f g mu equals 0?
You know, is this a philosophical question, or is it?
Yeah,
it's philosophical. Okay, so philosophically, it's because basically you want to get your needle decomposition as these equivalent classes on the strain of a literature function. So you're trying to kind of so the main idea was in theorem 1 is that really one literature function induce one D localization. Okay, on part of the space, but the point is, if you want to get a balancing condition, then that's where the how to pick this function u. That's where the motivation. That's where the point of view of optimal transport comes in. Sure. Okay, using the duality. Okay, so using the duality, you pick u as its maximized because you know that its gradient rays are going to solve the transport problem, meaning that you're going to get a balancing condition. Okay, so
but I mean, it's not the L2 transport problem, it's the L1 transport problem.
it's the L1.
I mean, that's the distinction.
Because of this duality. This important duality. Okay. One could even do something more general, but I mean, it's not written in stone actually. It has to be one, but you could do other things. So I don't know. My answer is not exactly not too clear, but at least I hope that at least you know, maybe not the reason why Florida was doing this, but at least what he was doing is clear. Okay. Okay, so I want to now spend the rest of the time comparing. Or before that, maybe I should say that very recently, about days ago. So is the paper on the archive? So is the paper on the archive? Okay. So Fabio Cavanetti and Gian Mondino extended archive. So Tao's result really uses what this theorem is completely, restricted to the manifold setting, the smooth setting. So Fabio and Andrea, motivated by Tartek's approach, point of view, but of course, to make sure what techniques are different, gave an analog of this theorem in a completely general CD row and metric measure space, metric measures, no smooth structure. But I think you need something like, you said, essentially non-branching. Okay, but it's very, very general class. And as you see, once you have this localization, we spent the first 2 days giving, you just get everything that was known in the smooth setting, in the CD row and case, whatever, isoperimetry, Minkowski, Sharp, so the four integral theorem, all of that stuff is now immediately applies to this very general, super general CD, not RCD, CD row n, essentially non-branching spaces. Automatically, you reduce the analysis to one dimension, that was essentially done in other works where it's elementary because it's one dimensional, so you can apply all the tools that you ever want in 1D. Okay, so all of that applies now to this complete generality using this one D localization. Now, I do want to compare this L1 method to what the L2 method gave us.
So, it's clear about the strain of U.
Sorry?
I mean, it's clear that n minus the strain of U has measure 0, or strain of U is in this method.
No, but you see where F, yeah. So of course, what U does on the set where F is 0, what F does, what U does on the set where F is 0 is irrelevant to the maximization problem.
Yeah, but when F is 0 outside of the strain of U, it's clear, or?
F is 0 yeah, because if it were not 0, then to get the balancing condition, you would need to pass the strain through it. Okay? And the non-negligible set and so on. Okay, if F is equal to 10 somewhere, okay?
The result of transportation.
If F is equal to 10 somewhere, then or if you want to do the optimal transport, so you have some positive mass here, you need to transport it to the other side, to some part where the function is negative. Okay, so it has to pass through there. The radiant, the optimal transport has to pass through there if it's a non-negligible set. Or if equivalently, if the integral of it has to be 0, so if it's 10 somewhere, it has to be balanced by somewhere else. Anyway, I want to compare what L2 optimal transport gave us in terms of the application, at least I'm interested. Okay, so it gave us a sharp Minkowski inequality. This was in the work of first Cordero, Kahn, Schmutter-Schwager, and then improved by Sturm definitely, which I like this very much. I think also logical to me. But anyway, this is sharp Minkowski inequality. You get it using the L2 approach. What else? We get a sharp, that's kind of numerical, but you get a sharp Poincare inequality on CD row n, row is positive. And n is positive too. I guess, so this was, to get just an inequality without the sharpness by using some standard factor, it's easy, but the sharp one was first done by Lot and Emanuel. And you can't believe that what they do give you something sharp. They do some crazy estimations that somehow at the end, they kind of look at the first order behavior and you get the sharp constant. And much kind of intuitive proof was given by Cordero. Actually, he doesn't use L2. He has to use this, not L1, but he uses optimum transport effect, a strange cost, very strange cost that he invents. Okay, but the fact that they managed to do this, a miracle. And so we also have that, and what we also have is, at least on our end, certainly we know how to use optimal transport to prove sharp isoperimetric, sharp Minkowski. So this is the Borel-Brass complete theorem. I'm just getting the first day using optimal transport, and if you know sharp Minkowski, you get sharp isoperimetric. But only isoperimetric reads inequalities on our end. But it does not give you, so this is yes. So this does not give you many things actually. It does not give you, for instance, the sharp log Sobolev. There's no known proof using L2 optimal transport of sharp log Sobolev on a CU1 space. So log Sobolev is, again, it's not crucial, but if integral of f squared is equal to d mu, then it's an equality stating that integral of f squared log f squared d mu is smaller than, that's going. So that's the sharp constant. This factor is what all the L2 approach misses. So you can get this result, done by Schlager, okay, but this n minus 1 over n is something which you very typically miss by, okay, you know, it's not a crucial factor for any application, I guess, except for the fact that you're not getting the right thing. It's annoying. Where does the method fail? We won't get into that here, but anyway, there's no L2 optimal transfer proof of that. There's no proof of sharp isochromatic inequalities as the one that I obtained. And I showed you on lecture 3 on the manifold setting. Sure, on a Euclidean setting, no problem. Borel rest complete. You can prove that using L2 optimal transport, but not on the manifold.
N greater than 1.
Sorry?
Greater than 1.
Sorry?
N.
Here, log Sobolev. Definitely. Greater than, let's say, topological number. Definitely. Otherwise, it's just false. Negative n is false. There's no log Sobolev. Let's see other sharp Sobolev inequalities. Under CU and so from Correa, you do get the right Sobolev inequality with the Sobolev exponent. You don't get using that. And many other things. Anyway, now all of these things are available even on the general metric measure space setting under CU and immediately because all of them localized, right? We spent the first 2 days now trying to convince you. So, for instance, you know. Anyway, this is exactly the type of inequality, two inequality that localizes. Sharp Sobolev can be a 4 inequality, 4 integral inequality. Isoperimetry, we also did this in the second day. How do you localize isoperimetry to 1D? So everything here boils down to 1D thing, which is now available because you can use the smooth 1D result. Anyway, so anyway, I have some more application. You can use L1 optimal transport now to prove various other things, which I worked on. Let's say obtain a general Grass complete using like a Buckner formula in terms of the boundaries. So now you can. There were some technical assumptions like the manifold have to be compact because if you're, let's say, solving the heat equation, solving the Poisson equation. You look at G on a manifold, if it's not compact, you run into trouble. Okay, so we assume in that paper that things are compact. Now you can get our generalized Grass complete inequality using localization. And various other things that I proved using the geometric measure theory can be now immediately localized. But anyway, I think I gave you enough applications. I mean certainly something that's less list. This is a very general tool to reduce the dimension 1, and maybe you also find it useful. Okay, thanks.
Are there any questions?
Do you have a reference for open problems in this area?
That's a good question. Certainly a reference, no. Many of the open problems, for me, I was interested in that. Well, we're kind of dead now. Using the result of Fabian and Jess, so, but still, okay, for instance, it would still be interesting for me to see proof using the traditional algebra approach. Okay, so traditional locality of entropy, or by using, even in the smooth setting, I mean, even using some Buckner integration, gamma 2 calculus, the tradition, gamma 2 calculus, of course, gives you that, but using optimal transport, you start with some, with the optimal transport map, the Vernier-McCann map, and you do the usual kind of integration by Parse-Schwarz. I would love to see if it gives you the right thing. That's an open problem. Otherwise, maybe. Yeah, I don't have a reference really. So, and somehow this is kind of very, at least in my mind, big breakthrough, at least in the metric measure setting, all these things are now, you get it. So.
Any other questions? Okay.
Let me also thank our gracious organizers for putting this all together. So Fabio, Michael, and Christian, thanks so much.
Thank you.